Alrighty, well, welcome back to another video. Today is Sunday, which is my cleaning day, so I've been working on cleaning, reorganizing, relocating. I relocated the hydraulic press up on them stands that the lathe's supposed to be on. You know, I need to get this more at eye level because I'm sick of bending over on my knees pressing something. So that took me a while to do. It's all bolted down. Fantastic, I love it there. So once I got all that done, I cleaned all the chips out behind the lathe. I cleaned the chip pan on the back, the whatever you call this, the shield on the back side. Took it outside, hosed it off, used simple green, got it all degreased. So this is all done, and the reason why I'm telling you all this is we're going to go ahead and mess this up again in this video, because we're going to do a machining video. What's that doing there? Machining video. I haven't done strictly a machining video in quite a while, but unfortunately it's kind of the same topic that I have already 2 videos on. But before you shut this one off, you got to see this first. Now what we're going to be working on is another Kobalt compressor regulator. And if you recall, and I'll put links in the description to 2 videos on this. The repair on mine, where the thing strips out as far as the regulator goes, and then you can't provide any pressure to the tool pressure side. And I did this repair, the initial repair, probably 2.5 years ago. It still works because I upgraded it. Pretty simple thing, but I used an existing bolt to replace the actual shaft that this knob is attached to. And so I kind of did it not fully machining. I just did a little bit of machining. Well, let me show you what we got right now. I gotta walk around here. We got the door closed because there's a cold front coming. So an air compressor regulator from a Kobalt, just like the air compressor I showed you before, garden variety, is overall in pretty good shape. The gauges look good, nothing's banged up. The gauge glass, whatever you want to call it, that's not damaged. Usually these things get smashed. But when I opened the box up and took a look at it, and there it is right there. This did not happen in shipping, I don't believe. This is snapped off. And obviously, and I'm like, you got to be kidding me. I've never seen something like that snapped off. Now, there's a couple of reasons for it, like for example, that part of it's hollow up there, or it's just a piece of crap material. This is obviously Chinesium peanut butter material. But if this had happened in shipping, this would have been a hell of a lot more stronger, at least stronger in some respects, than the gauges themselves. They'd be all banged up, and they are not. So it leads me to believe this thing snapped off previous to that being shipped to me, which is from a viewer subscriber. So that's why I'm filming this one. Previous iterations of doing this on videos used existing parts and modified them to fix this. But in this video, we're going to machine everything we need to fix this. We're going to make a new shaft for this and single point thread it in metric. We are going to machine an insert that goes inside this aluminum, a steel insert, because I have a drawing for it. And we're going to make everything that we need to do to make this. So that includes any threading, that includes any drilling, turning, and that sort of thing. Assuming we can even get it apart, because usually that's the biggest problem. I think it might be interesting from a machining aspect only, not necessarily because it's something we've already had on the channel a couple of times, and we're going to machine our way out of trouble here and hopefully get this back into working condition. So let me get you set up and we'll try to get this off and see if we can look inside there. And I suspect this is all galled up in there, which is fine because we're going to drill that out anyway and do our thing. One advantage to not having the knob, I could go somewhere with that. One advantage of the knob being not there is the fact that I think we can get a socket on this. Basically, if there was a knob job in place, we wouldn't feel to slip our thing over the knob job. But in this case, because it's got like a 12-point type flat, it might work. A lot better purchase than usually I end up using a freaking universal wrench like a vice grip or channel locks. I'm going to try it with this. Now, if I had a 12.29 mil socket, I think it would work better. I don't have one. They go up. My 12 points go up 27. Everything after that's all 6-point. I'm just going to try it this way. This 1.1 is not a very good fit for it, but you never know. I might get enough purchase. We're going to heat it a little bit too. These are typically really, really stuck. The lathe does not have a spindle lock like a true spindle lock, but we'll use the Chuck key. Chuck keys in love. Chuck in love. And then we'll go ahead and put it in the lowest range, give us an advantage. I believe there's a rubber diaphragm thing in there, so that's why I'm using a pencil dick torch right now. And I'm holding in the chuck jaws for obvious reasons. I figure by now you figured it out. It's very difficult to hold this in a vise and not twist the thing up like a pretzel. Try that. I honestly don't think this is going to work, but we'll make something work eventually, I hope. Oh, look at that. No, it is working. Son of a gun. Wow, just a little bit of heat. Let me tell you what. Makes a world of difference. Before I get that all the way out, hang on. Let's get some blaster on it. So yeah, all right. This is a good way to hold this in a chuck. All right. I'm very happy that we were able to do that. It's not even that warm. There is an O-ring behind here. I usually can reuse it. Okay, so there's the offending piece with the O-ring. There's this little diaphragm thing which looks like it's absolutely stuck in there. Oh, actually it might pull out. Yeah, it might pull out, but hopefully it won't take too long. You take too long to pull out and bad things can happen. This guy pushes down onto that diaphragm down inside here to regulate the pressure. I'm not going to go into exactly how this works because my other videos do, but I just wanted to mention that. This is the main thing we're going to be working on besides making a new shaft for it. Guys, we must be living right. That's coming right out. I think the problem is it is stripped out, yeah. Take a look at that. When you back this out, it's not doing much of anything. How this thing broke, I don't know, maybe it did break in shipping. You know, it is peanut butter parts, as I said. Actually, I said Chinesium peanut butter parts, but you get the drift. Almost. There it is. So, here is the bottom end, the business end of that shaft, and then the other one inside the knob. It isn't terribly long, you know. It's a fairly short little shaft. We have to duplicate that. The main problem is getting this one out. Now what I did in the past, because the shaft was out a little bit longer, of course, full length, I was able to somehow direct heat into this. That melted the plastic around where this is set in. That's how they put this together anyway. It's kind of melted around it. They heated this thing up and shoved it in, and it's got like a knurled end. Kind of like a knurl, you know, typical to what you see embedded in plastic. We're going to have to reverse that and get this out somehow. So I don't even know how I'm going to do this, to be honest with you. But we need to be able to get a purchase on that, you know, screw something on it. And that is an M8. I think we're going to go over to the lathe and we're going to make ourselves an M8 sleeve. Once we get this out, we're going to start working on the other stuff. Okay, this is a piece of steel that used to be, you know, your fireplace grill grating, whatever you want to call it, you put your wood into. We replaced years and years ago, and I cut that thing up into usable pieces, and I've been going through it for about the last 6 years. In fact, there's a piece of this on the sidecar rig, in fact, from way back then. And then we'll drill and tap it for M8. Let's run her at 800 RPM. Yeah, why not? Better. This is good steel. I'd say the way this is cutting is probably, they use 1045 maybe on this. Well, there's a center in there and it's not running true, so let's cut that off. That's close enough. Tell you what, that is good steel, whatever they make those out of. Okay, a tap drill for an M8 1.25 pitch is a 6.8 mil. I don't have that, but an Imperial, It's a letter H drill bit, 266 thou. The conversion is actually 267 over to imperial. I think it's close enough. Good enough. Good enough. All right, now we'll tap it. I didn't bother chamfering it. We can always do that afterwards. I don't know if we'll even need to. The threads inside that knob may be completely chowdered up where we can't even get it to start. So I don't know what we'll do at that point. We'll figure something out. Slow. Don't need to do this fast. Well, okay. If you say so. Probably enough anyway. Let's see. So let's look at this again. Why is there a hole in the middle of this shaft? It doesn't go up to the end. When they drilled this to tap the hole for that screw that goes in the end of this, they went really deep, and that really weakened this thing. Let's part it off then. Good. All right, so a more civilized way to hold this knob is in the lathe, because you put it in a vise, it's almost impossible. We got 3 jaws, 3 points of contact. It's a lot better. That way we can kind of give this a good yank. So what we're going to do is I'm going to put a piece of aluminum up over top of this. Assuming that I drilled it out to the right size, which doesn't appear that I did. Yeah, it's had a burr on it. That's better. But before I put this on, I'm going to take some of this carbon fiber. It's from like a carbon fiber type fire blanket thing. And I'm going to put that on first. I'm going to slip it on over with a hole in it. And then we're going to put this on here because the aluminum's going to want to wick heat. And I don't want that contact in the plastic. The aluminum wicks heat, who cares? It's not going to go anywhere. So let's go ahead. I got a pair of vice grips. Yeah, these Viceroy grips should work quite nicely. Okay, let's fire and hole it. I'm sure you figured it out already. We're indirectly heating that broken part via the sleeve inside, letting the heat wick in there. Hopefully it'll get warm enough where we can melt the plastic and pull it out. Not quite there, but it's moving. A little bit more heat. It's pretty hot now. Give it a chance to wick in there. Yep, there it goes. Haha, got it. See? I had to give it a few moments for it to wick in. So that's that end there I was talking about. Looks like a knurl. That's where we're going to end up having to make something similar to that. I got to go look at my drawing. Let's pull that out now, because I can't remember what I've made these in the past, actually. Because that'll tell me the thread in the sleeve, and ergo the size of the shaft we need to make. Oh, and by the way, here's the inside of what we just pulled that end of that shaft out of, so you can see we didn't destroy it. So we can't make the next one the same size because it's already been pushed in with heat, or molded around it, one of the two, same difference. So we'll make the end of that a little bit bigger. I'm not really sure yet how much, and then put some sort of a feature on it, probably just a knurl, or I don't know, we'll figure something out. Okay, I found the drawing. Had to look twice, but I did find it. This is the sleeve that I machined to go inside this aluminum housing right here. I thought it was M10, but we're going to make an M8 shaft. So it's pretty much duplicating what it had, but we'll make it better. The OD is 1/2 inch for 1/2 inch 20 fine thread, because I happen to have a 1/2 inch 20 tap, which will go right through here for that. And then we'll single point the 1/2 inch 20 on the outside. Tap this first, and then just use this as a guide for that single pointing. And then we do a little lip on the end of it, so it won't just push all the way through. Put some Loctite on it, Bob's your uncle. And I'll read my notes here. It's face off 0.25, 0.025 plus or minus 5 thou off the outer edge of the aluminum regulator body before installing the insert to accommodate for width of the lip stop. Otherwise the OG screw won't protrude into this as far as it should. I remember that now. If you don't face a little bit off, because of that lip, which doesn't cause any interference with the knob. The screw won't go down all the way. So that's part of it there that I'm just remembering now as we look at the drawing. All right, let's get our little Mr. Peanut Butter part here chucked up, and it should run fairly true. Oh yeah, that'll be fine. And the tool loads are going to be a minimum because, like I said, this is Chinese peanut butter metal. So far, so good. Okay, tap drill size, 1/2 inch 20, 29/64. This material isn't very wide in here, the thickness on the Z-axis. So that's why I picked a 1/2 inch 20 fine thread. And 1/2 inch is much larger than an 8 mil, which is around 5/16, so 312. So because we're making an insert that's got threads cut into it, to accommodate these ID threads, we got to make sure we got enough clearance between the thread we're going to put in for that shaft we're going to make and the insert that we're putting in, which is a steel insert, which is going to solve this whole problem. The whole thing is you got to get away from this aluminum as far as that thread that goes through to push on that spring. That spring is pretty tight and pretty hard, and so it puts a lot of stress on these threads no matter how you lubricate them, because it's Chinese peanut butter material. The damn thing just ends up stripping out. I'll try not to go on a tirade, but I'll give you my opinion on this. This is designed obsolescence of functionality. This is designed to fail. It's really unfortunate and inexcusable that Kobalt, whoever built it for him, let this go this way. It should have a steel insert where that running surface of an M8 thread goes, not aluminum, especially peanut butter aluminum. So after a certain amount of duty cycles, the thing strips out. It's designed to do this. So I find it inexcusable and unacceptable. I don't know, I'll run it through at 600, I think. Why not? If I might indulge your attention on the chips and the look of the chips that are coming off of that drill bit, they are absolutely stringy, just absolutely terrible looking chips. They're not typical aluminum chips because it's not aluminum. Most likely it's pot metal. Some peanut butter junk made out of scum water, dead bugs, dried up seaweed. I don't know what it is, but the crap is just absolute junk and unacceptable that they use this. There you go, that's it. That's all there is to it. Now what I have noticed is there's some inclusions on the aluminum. In other words, there's one right there. I'll show it to you. This is how shitty this crap is. I mean, you can get that blown out. The material, I don't even know if it's aluminum, some sort of pot metal, I'm assuming, but let me zoom up if I can with these gloves on. You see that inside there? That is not a chip laying there. That is an imperfection in the material. It's just absolutely junk. So you turn it around there and it's not there. You go over here and it's back again because it's an inclusion, like a casting inclusion. Absolutely junk. Oh, that's beautiful. I'm liking that a lot. You can just see it's like a big hole in there. But you know what? It's enough threads to do what we got to do. So now we got some good threads in there for an insert. 1/2 inch 20. Okay, this I believe is 3/4 inch, 1045. I know it's 1045. I bought this material specifically for this down at Metal Supermarket a while back, probably over a year ago. But I've been picking at it, doing other things. But I got a 3/4 inch so I could make these 1/2 inch inserts. That lip that I mentioned before is on the inside here because obviously we're cutting from right to left. And so we'll leave enough length for that when we part it off. But essentially, we want that lip edge to be slightly larger than the major diameter of the thread, which is 1/2 inch. So I have this at 515 to 520. So we take it down to 520 to start, and then we'll take the thread size down to a 1/2 inch. feeling I need to change this. Yeah, I'm gonna switch this insert over. I'm gonna rotate it. It's a new insert, but I've already burned up this one side of it, so let me do that off camera. I can tell why it's cut and it sucks. I was just looking at my drawing, and I wrote down on the drawing here the compound in feed. I'm at 29.5 degrees. Is 33 thousandths on the compound to reach the minor diameter, or the pitch diameter of that 1/2 inch 20. I don't remember doing that, but I must have. That's better. Oh yeah. We're shedding high cotton now. So 520 we want to go to. That'll do it for our work area. There's 200. Should be around 550 then. Yeah, 550. I was right. Okay, 540. Close enough. 541 on the micrometer. 3041. So 20 thousandths. I just want to make sure that I'm not going to blow this one. That's 530, so we got 10 thousandths to go. Let's do another 5 on a side. Should be about there. 520. Again, we want to go big. 521. Okay, so the total length of this insert that we need to finish it out at is 0.300, just under 5/16. Obviously I made this pretty long because I just needed a longer working area. But as far as the turning up to a 1/2 inch now, what we're going to do is we're going to run this up to about 400 thousandths instead of 300. And then we'll leave that lip, which will be at the end here, which we'll get that done when we drill and tap this thing. And then we part it off. We'll essentially make the width of that lip, which is about 20 thousandths with the parting tool at the appropriate location. So then, you know, before we part it off, we're just going to pick up on that lip, and then we're going to come back and face it off to a total of 300. I think that's the safest way to do it, because then we don't risk having to make another one. We don't risk screwing it up. Well, you see what I mean. So let's see, we're at 520. We need a 1/2 inch, 10 thousandths on the side. $400. There's 400 right there. Couple of thou under, but I don't care. It's all right. It's close enough. I'm not going to do any chamfer or anything because we need to face this off anyway. We're going to thread up to that step that we're going to leave, or the shoulder, I should say. Very close to it at least. So we are going to, I don't even think we need a thread relief, but we may end up putting one in, and then we'll just thread up to that. Okie doke, we got ourselves a fresh edge of the insert. I rotated it around to one that's more appropriate for a fine thread. I already squared the tool against the tool holder, against the chuck with 1, 2, 3 blocks. So what we really need to do now is just normal threading operation. You've seen this before. See, this is how I do it. I zero out the DRO, zero out the cross slide, and of course zero out the compound. We're going to advance on the compound though, as far as taking a cut, but we always have to come back to this. If we're not on this and that's not zero, I check one against the other. Then if I'm off one full turn, and we either bite the part or we're not cutting anything. So it's just kind of a sanity check for me. We'll touch off and get zeroed out. It's a fine thread, so it's not going to move that quick. Okay, we're touched off. We'll make a scratch pass. Whoops. See, I got confused and I hit the damn wrong thing. I cannot believe I just did that.
It's a very common word.
Well, I scrapped this part. All right, we're in do-over land. As I've said many times, I don't hide my mistakes, and it's really easy to screw up threading, you know, because it's kind of a complicated operation when you think about it. You got to do a couple things in a certain sequence, repetitive fashion, and if you don't, it gets screwed up. So I'm back where you just last saw it before I screwed up. 520 over here, I just cut it back a little further since I already had a 520 to go off of, then just eliminated the part I screwed up. 400 thousandths in at 1/2 inch. I'm going to run it at 200 instead of 360. It's a little quick for such a short amount to thread. I think that's a little bit more reasonable. So let's try that. Maybe we won't screw this one up. Let's put a thou or two on it. I mean, normally I'd put a little blue on this, but I can see it pretty good. Oh yeah, it looks like 20 to me. Okie doke. Then put some Earl on her and start cutting some thread. I was thinking before we don't need to put a chamfer on it, but kind of do. All right, let me come back to 0. Compound says 30. These are crested over quite good. So let's go ahead and just back off and see how this thing fits, if it does at all. Yeah, she's tight still. Okay, she's tight. Do a spring pass. I'm showing I have a mark on my compound. It may be from the last time I did it, but this is perfect anyway. Oh yeah, there's barely any play in that. It's long, so you know it's not going to want to go on all the way. It should, because it's, oh there it goes, because it's a through hole. That's perfect. Yeah, baby. All right. Now before we do any more, I'm going to go ahead and drill and tap it for M8. You know, which is quite handy to do right now anyway, because I got the M8 tap and tap drill laying right here from making that little sleeve before to get that broken piece out of the knob. So might as well just do it right now. Make it, it doesn't have to be that deep, but we have to make it at least 400 thousandths. I really do enjoy single point threading. Even when I screw up, I enjoy it. Because I don't know, for some reason it's strangely satisfying to see a blank piece of material and in short order you got a nice thread machined into it. Much nicer than I believe that you can get from a die. I got these tap sockets the other day. I have never had a set of them. And I needed to tap 3 holes on that Valkyrie frame for the upper engine mounts. 3 of those holes were stripped out. First time I've ever seen that. The bolts were scrap. I had to replace those, what I had on hand. They're M8. And I could not get a tap wrench in, you know, to make the swing. So I had to go straight in. And the helicoil tap that I had, I didn't have a tap holder for it that would actually fit it. So I said, shit. And I looked online, and Advanced Auto Parts had a set of these. They're Lyle brand. And so I went over and picked them up and got some more helicoil inserts. Actually, I bought a whole kit so I'd have a new tap too. And I fixed them. I would have preferred to use a time cert, but I don't have M8 time cert. So the best we can do, right, is what we can do.
Oh no! Not this shit again!
Okay, we'll bring it to length now. And we'll zero that. Back out, go up 20. I'm just gonna bake it in this way instead of doing the math. Come out 300, that's the total length of it, according to my drawing. Ah! I got a little bit too feisty. I just freaking chipped another damn insert. The best thing to do on a thread really is to come in on the Z-axis and cut in and then go a little deeper and cut in and so forth. Because if you plunge in on a thread with a carbide insert, it's almost guaranteed, whoops, that you are going to chip an insert because it picks up on the thread. It's stupid. Be better off doing this. And then we'll leave about 10. Come in a little more. Once we get below the thread, then we can go in. Beautiful. I'm just going to go ahead and chamfer that with a file. I think that will be just fine. And instead of putting the chamfer tool back in with the chuck, we'll do it the no-go route. Good enough. Okay, I did that thread relief off camera. And then we're going to touch off. The width of the parting tool is 78 thou. We'll move that in from the edge so we're on this side of the tool. Go in 300 and our 20 thou lip should still remain because we baked that in before. Okay. Good enough. 0. 0 again. Now we're on this side of the tool. Back out a lot. 300. That looks about 20 thou right there. I think that's good. We'll go ahead and lock the carriage and proceed to probably destroy the part. I think my parting tool is dull. Okay. Yeah, I think the parting tool is just a wee bit on the dull side. Okay, there's our insert. You can see how thin that little lip is. Let me get this cleaned up off camera and we'll go ahead and get this inserted. All right, we're going to assemble this. This is the final product as far as the insert goes. I just used the belt sander over there and knocked that down and re-chamfered it and ran a tap back through it because it leaves a burr. Same on this. Everything's good. I mentioned I was going to use a M8 with a nut. I don't need to use a nut because this is a shank bolt, so I'll just run it up to the shank and tighten it up with that with some Loctite 271. High strength. This has all been degreased with some brake clean. So let's go ahead and get it on here first. She's like beautiful as far as this thread goes. This M8 thread's perfect. It's going to be great for what it's intended. And I don't know if I mentioned, I did take this down 20 thou. Faced it down. That's why I had to run a tap through it again. And so it should be exactly right as far as protrusion goes. With Loctite 271 on it, it should be no problem whatsoever to staying in there. But a healthy amount on this. It's really got to stay in there. A good cinch like that. Okay, we'll let that bond a little bit and then we'll be able to back this thing out no problem. Took about 3 minutes to get that hard enough where I can just back this out because it was still pretty tight in there. Okay, so there is the repaired other half, the outside half if you will, of this regulator. And since this part's all good, we got to clean it up a little bit. This is definitely going to work. I think she came out great. The telltale sign that this is going to work good as far as protrusion goes is we're flush up here and we're like dead flush in there. So in other words, it's not recessed down inside there from this direction, nor is it proud. It's like right on the money. We need to work on making a new one of these next. Piece that was inside the housing, you know, the one that was broken off inside here. Remember there was a screw on the inside of it? Well, that's this screw right here. I got this screw out. We're going to need that. So this is the tail end. This is not the end from the knob side. But when you add the two of them together, I'm working on a drawing over here. In fact, when you lay these together and just measure them up, so we're just under an inch nominal on the end to end. And when I write nominal is I may modify this. Also overall on this, it's more, not really a knurl, it's more like a spline almost. That major diameter is 400.400. And then so this section here is how much? Well, I need to measure that, but what I wanted to show you first was, take a look at where all that metal is that used to be the threads where this was screwed into that housing. I was just about to measure and I go, oh, I got to show them this. Look at this. This is the threads. This is that peanut butter material that this piece of crap is made out of. It's just amazing that Lowe's just had no conception or conceptual understanding of how crappy some of the junk that they are pushing out their doors was and is. I get 358 thou as far as the thickness of this head goes when I measure that out. What that is in metric doesn't matter because I work in imperial. What does matter though, that this 400 thousandths nominal on this overall diameter here is what we're going to make it ultimately, because if I make it the same size as this and I go to shove it in here even with it hot to melt it in, it's not going to work. So I have to calculate how much bigger I want to make this and how I'm going to make some sort of a feature on it like this spline thing. I don't have a tool we can use radially, knurling tool. That's a radially applied tool, but I might be able to longitudinally do some scratches like this, almost like using your lathe as a shaper. We might try that with a tool and just make a random these lines, and I'll show you what I mean on the z-axis when we get to that point. That may be our best bet. And then we'll just make this bigger by, I don't know, 50 thou or so. We'll make it 450 instead of 400. That should be enough to fill the gap in here. There's plenty of material in there for it, so we should be good. And I think I'm going to use bronze. Let's go over to the lathe and we'll start working on this and I'll explain my rationale. Okay, so here's my logic. Here's a piece of bronze. I have it in stock. It's easily machinable. I believe this is the grade that's designed to be used on running surfaces, you know, to make little bearings, bushings, and things out of. This is definitely a running surface. It is a thread, yes, but it's not a thread that fixtures something where you tighten it up and leave it. And I think this would be an excellent material for this. Now, we could certainly do 1045 on 1045, no problem. We would definitely not do stainless on 1045. That'll gall up in a New York minute no matter how much freaking grease you got in there. Only an inch long that I need, so not going to really be consuming a whole lot of material money-wise, price-wise. And yeah, I think it'll be a good experiment. Okay, I took the liberty of changing the threading gears around. Changing the change gears, that's a good way to put it, huh? And so we're over to the metric gears that I can cut a 1.25 pitch. So the first diameter we hit is that larger diameter of that head, which is 400 nominal. We're going to 450. So let's get going. And there's your main problem with bronze or brass. It goes everywhere. We're 5 thou above it. We're just going to leave that. It's close enough. This is absolutely a non-critical dimension. Just bigger than the nominal is fine, because we'll figure out what we're going to do with that head after that. So you said head. I got a phone call, hang on. Go ahead and cut the diameter for the threads, which of course is 8 mil. As far as the length up on the z-axis, the length of the threads itself, it's only 584 thou, so it's just a little over a ½ inch. Then I'll figure out what we're going to do to kind of profile that head. I got an idea for it, which we can actually do while it's in this setup. That's a good point. We don't have to mess with anything. We can leave it in this setup, and I'll show you what we're going to do about that, because I got kind of a cool idea. Because this is going to be a running surface, you know, the thread is going to be running in and out, I do want a close fitment. Yep, can't get better than that. 312 on the button. Okay, first thing I'm going to do is take the threading tool and kind of chamfer this edge back. And we'll go ahead and chamfer the front one here. Just a little bit. There we go. And this does look very short, I realize that, but that is the length that it measures out to be. It's longer because a screw goes in the end of it, so if it's any longer or any shorter, it doesn't work right, and it looks stupid, and you gotta wind the thing 100 freaking times before it actually starts pushing the spring into that doodad to actually do its regulator magic. Ooh, I'm glad that's over. So, there we go. I've just, you know, I haven't done this a lot, but I've done it enough to realize what works and what doesn't. Touch off. Right there. All right, beauty, we're back on 0. Let's take a look. Yeah, looks 1.25. Okay, let's cut it. Let's get prepared for battle. Whoa! How the hell did I go that deep? I bet you I totally screwed this thing up. Yep. I just blew that right out. Yep, I screwed up. Again, I don't know how I just did that. All right, we're back where we were. You know, I needed to remake that piece anyway. There was a hole in the end of it. I did see that. I thought I had cut enough of it off, and I kind of assumed that it was going to be small enough for a tap drill for an M5. There's no way. That was big. That was way big. We had to remake this anyway because I was stupid. But then I was doubly stupid by I must have not had the thing zeroed properly and trashed the thread. So let's try that again, shall we? That's a lot better. That's okay if we touch that. Just starting, so we gotta go a little bit more. See how badly we can screw this up. It's not gonna take much to get us there, I'm gonna tell you right now. Best thing is to know the theoretical depth for the root of the thread, but I don't have a way to look that up. I don't have a machinery handbook, so best I can do is just kind of trial and error, T&A. That's better. Yeah, it is a little looser than I wanted. I shouldn't have taken that second cup, but it feels good. I mean, I really like the feel of that bronze on the steel. I think this is really a good idea. Went a little bit more than I wanted to, though, but not bad. I mean, just a little wiggle.
No! God, please, no! No! No!
Okay, I took this broken piece and put it in the chuck just for a minute. Used the threading tool, just like you see it, turn on its side. And I lined it up to these grooves, just a couple of them, and then made a mark on the spindle nose part, D1-4 spindle nose, and lined the mark up to this yellow line. Just kept going around 3 or 4 times. Then I got a pattern. I just used a scale, you know, a flexible scale like this, and went around 360. It's not accurate, I don't care, but it gives me a place where I can put the spindle. We're gonna carve some of those grooves in just like this, approximately the same depth, just like on a shaper. All right, we'll set a 0, that's good enough. I'm just gonna go around in time warp and do this. Make sure we're clear, yeah. All right, here we go. This is done, but I have a question for you. How much does bronze cost nowadays? Bronze bar stock? Pretty expensive. So you already saw I screwed up 1. What if I told you I screwed up 2 and this is the 3rd one? You'd say, nah, you couldn't do that. I sure could. I broke this one because when I parted it off, I forgot to do that groove in the middle like the original one has, I guess for the plastic to go somewhere. And I put it in that little collar I made to pull the original one out of the knob itself. And then I spun that and hit it with the parting blade. That was a dumb mistake. Only that much of it was in there, snapped it right off because it's hollow there. I took the opportunity to make this thread a little tighter and also a little shallower on that 5mm hole, 5mm threaded hole on the end. So this is going to be it. And it does fit wonderfully in that body, which I'll show you here in a minute, that housing. The reason why I asked how much bronze cost is, remember that was about a 6-inch piece? This is what's left. I tell you what, I'm gonna have to order more of this shit. You gotta just laugh sometimes, because if you didn't, well, if I didn't, I'd be crying. Okay, I don't know if this is gonna work, but whatever it is, it'll be straight. Excuse me, I have no idea how hot to make this thing, so I got no idea. I think I'm just gonna wing it. Here we go. Fire in the hole. Hope I don't melt it. I don't even know what the melting point of bronze is. It's probably pretty low. Let's try that. I know you can get it red, and that looked like it was getting started to do that. See what it'll do, if it'll go. I'll be able to feel it. It should smoke too. Oh, there it goes. Yeah. All right, we should be at the bottom right there. Let it cool and see what happens. All right, folks, it's time to put everything together. See how we did. But first, I want to show you this. This came out fantastic. You can see how melted it is down inside there. It pushed all that material out of the way because this is bigger than what was in there. But this is the part that's the best. If I put this back on, this sucker is freaking in there. There is no way that's moving. The only question I have is whether or not I pushed it in too far, you know, because the relationship between the tip of that and this body might cause some interference, but I don't think I did. I pushed it in until I felt it essentially bottom, seat in there, and then let it cool. But boy, did that work. Wow. It looks fantastic. So I've already brake cleaned the hole where this 5mm screw goes because that's got to get Loctited after we put it through. I think I forgot to mention to you what that's for. It's not just to hold, well, the only thing really it is for is to keep this from backing out of the body all the way. It's a slightly larger than the 8mm major diameter of that thread. It's essentially a stop. So it can't go through all the way. It can't pull backwards from the inside. So the first thing we're going to do is grease her up. Go inside here. Put a little bit inside here as well. This has got to be really well greased. Oh wow, that's so smooth. There's like virtually hardly any movement on that. That is fantastic. And of course I got grease right down into my threads there. Let me clean those out again, stand by. We're going to use some of this blue Loctite, non-permanent thread locker. This is fine for something like this, but we're going to put a generous amount on there. But when you put this on, if it starts smearing blue Loctite around the outside of it, we got to wipe that up with a Q-tip first so it doesn't get drug into these threads. And nice and tight. I've never had one loosen up, so I don't think it will, but I just want to make sure that we're not going to get any funny business going on there. So it only will go out so far, then it bottoms on that. That's what keeps it from doing that. Boy, is that smooth. Wow. That's way better than any one I've ever done before. Okay, we'll put the O-ring on. Okay, next goes the spring, but first, a little dome guy goes in there. We'll put a little grease on top of that screw where that dome guy sits. Why not? Just like that. Then the spring. Then this goes in, which we got to grease up and put a little grease around the inside of this this particular body. This really is like a cylinder for this, if you really think about it, and that's the piston. I called it a diaphragm earlier. That's probably wrong. I know it's wrong. I think the diaphragm's inside here. That's what I was referring to. But as usual, I screwed it up as I usually screw everything up. The tit goes out because it goes into that diaphragm thing down in there. Oh, that fits perfect. That looks about right. Okay, so the next and the final step is to insert it inside the regulator, which I've all cleaned up here real well. Now, I don't really want to trust this O-ring 100% because it's a piece of crap. You know, it is Chinese junk. Let's back this out, why don't we, and get this thing down where it's supposed to be. There we go. We're going to put some 3-bond 1270B on this, just on the threads a little bit, and help it seal off, but I just think it's the right thing to do. I just have a feeling. There was most definitely some kind of sealant or pipe sealant or pipe thread sealant or something inside there. When it came apart, I could tell. Final assembly. Now, torquing it back up, I think I made some sort of a wrench out of one of those thin junk wrenches you get with like furniture purchases and things like that. I think I got one. All right, let me see what I can find to tighten that up. All right, we're going to test here. Got a nipple established on the inlet side, and it's always good to establish a nipple. And I tightened this up best I could with a pair of, long nose vice grips. You know, a couple of dings on it, but there's nothing else I can do. I thought I made something, but I can't find it. And I'm looking at these gauges. Ultimately, they do look a little bit banged up, so I hope they have clear swingage in there, but we'll find out now. This is backed all the way out. My air compressor regulator is turned up to nuclear. You can see this gauge is giving us accurate reading. Oh yeah, look at that. So we're maxed out at, see, this is what I look for. When I turn this up, I want the tool pressure to reach the tank pressure well before this thing bottoms out, because say you go up to about 90 or 100 psi and then this bottoms out because of that offset being wrong on that screw or something, you're not going to be able to get maximum pressure on the tool side here, or these two. Back off again. So there's 120 over here, just a little over 120. Now we're approaching 120 on the tool gauge side. And this thing will go 1, 2, it'll go like 3 or 4 more turns before it bottoms out. So that was full right there. Now it's absolutely full. What it'll make a difference in is volume. Yeah, the other thing we want to make sure is that it's closing off when there's no pressure on that spring. So now I have a tool in here. That's what I use to blow out some caliper pistons sometimes. Not recommended. It is very dangerous, but I'm a professional.
That is total bullshit.
So with it all the way off, nothing. Now let's just hold that on. We're going to start cranking a little bit. Perfect. Now we're starting to get flow. All right, turn that off. Now it goes up to 120. But where does it go when you open it? I just barely reached 120 on this. So, see how far it drops down? So let's go another turn. It goes to only 90 at that point. Go another, well, that's actually half a turn, sorry. Goes down to about 95. Another half a turn. And another half a turn. And that's the maximum pressure that this can generate in this setup, because it's being supplied by a long pressure hose. That's a 100-foot hose, or a 50-foot hose, I'm sorry. So this is maxed out. Drops to about a little over 90 from 120 on this gauge when you fire off full flow air. Maybe a little bit below. But again, that is the delivery, because if you look at this one, so the fact that these two are exactly the same when you run this wide open, when this thing's turned up all the way, tells me that we absolutely are opening up 100% before we stop, well before we stop, the cranking stop that is. Therefore, this thing is going to be fully functional. And it's probably one of the best ones I've ever done as far as the feel and how it came out. I really like the idea of using that bronze for that part in there. All right, time to close it out. That's it. Hope you got something out of it. I know it's a redo or a do-over of 2 other related videos, but we did machine our way out of its trouble with a 1045 sleeve in there, or I should say fitting, and a bronze shaft going through there, which is really designed for running on steel like that, plus all that freaking grease. This thing ain't ever going to fail. The innards of this diaphragm, that could certainly fail. The whole thing could be scrapped. But as far as the mechanical aspects of activating that diaphragm, this is never going to fail. I almost guarantee it. Unless it's hit or something like that, which segues me back to the packaging of this. The packaging absolutely sucked now that I look at the box again. So that's it. Hope you got something out of it. I sure as hell did, and I had a lot of fun doing it, except for the fact now I gotta clean that freaking lathe up again. So stick around, you see more videos. As always, thanks for watching. Don't just repair, restore. We'll catch you on next video.